right, hello everybody. So today we are going to be doing the chapter 12 notes, starting them on trigonometry. And I'm recording this outside, so it might sound like there's some animals and such in the background. All right, for trigonometry, today we are going to start with trig ratios, section 12.1. And our objectives today, come on pen, are going to be to look at the trigonometry ratios for sine, cosine, and tangent, and then understand how they're useful. It's going to be some new vocabulary and something that you've probably never encountered before, so make sure that you're giving it your full attention. All right, trigonometry is the study of the relationship between the sides of a triangle and the angles of a triangle. So we're going to be comparing angles and sides, but specifically we're going to start off with right triangles. So this is often abbreviated as right triangle trig. All right, when we have similar triangles, which we looked at on the last unit, we're going to have the same ratio when we compare their sides. But that's also because with similar triangles, remember the angles are going to be congruent. And so if the angles are congruent, we're going to have ratios comparing corresponding sides that are going to be the same ratio. So for example, on this one, we can see we have a height of 3 and a base of 5. If I look at the next triangle and compare those two same things, we have a height of 9 and a base of 15. The next triangle, height of 6, base of 10. And then our final triangle, height of 33, base of 55. Now these are all similar triangles because of the AA similarity conjecture. They both, or all of them, have a 90-degree corner, and they all have a 31-degree angle. And whenever you have two congruent angles, it automatically means all three are congruent. And with that, we have 4 similar triangles here. So if I were to take this 3/5 and simplify it, that one is already simplified. If I were to simplify these other fractions, 9/15 reduced would equal 3/5, 6/10 reduced would equal 3/5, and 33 out of 55 reduced would equal 3/5. So all of these ratios are going to be the exact same. And again, there's going to be a relationship between the types of angles that were given in the triangle and these ratio sizes. So what we're going to be looking at here is on a right triangle, we have 3 sides that are all related to the position of the angles that are given. So here we have a 90-degree right angle. Anytime you go across from that, the side across from that is going to be called the hypotenuse. We abbreviate that side C. All right, now for this purposes, typically thinking about Pythagorean theorem, we would say like a squared plus b squared equals c squared. But for these abbreviation purposes, hypotenuse is kind of a long word to write out. So I'm going to abbreviate it with a capital H for hypotenuse. All right, now this guy here up in the corner looks like a 0 with a slash through it. It's actually the word theta, or the Greek symbol theta. And theta is kind of like a variable x, where it's just a placeholder for our angle measurement that is possibly not given. So when we're looking at that particular corner, and I want to compare the sides that are given, across from theta is going to be the opposite side. So down here, this is the opposite side. I'm going to abbreviate that with an O. And then the side that is next to theta and next to our right angle is the adjacent side. I'm going to abbreviate that with an A. So we're going to be looking at these three sides according to where they are placed when you have a right angle or a specific angle measurement on a right triangle. All right, over here it says, because the ratios for certain lengths and angles will always be the same, we can calculate the missing side lengths given an angle and one other side on a right triangle. So if I think back down to the triangles down here, it's nice when we have two triangles to compare with. And let's say that this 9 right here was actually our missing value from our last chapter. We could set up a proportion and we could cross multiply using these two ratios to solve for x. But oftentimes we're just going to be given one triangle. Let's say we were given this guy, and maybe the 33 was missing. And because of the size of the angle 31 and the position from the side that's missing and the 55 side, we can use specifically assigned ratios that always occur with a 31-degree angle on a right triangle. And these are already pre-programmed into your calculator. And so we just have to be able to use the right calculator buttons to say, hey, what was that ratio? And I want to use it to solve for this other guy that's missing. So there's a trick to remember this, and the trick is the abbreviation SOHCAHTOA. Now, SO is the sine function. Right here, this S in SO represents the sine function, and then the O and the H represent those opposite and hypotenuse sides that we abbreviated before. So I'm just going to abbreviate those again on this picture. Here's our given angle theta, and if I look across from that, I can see that this is the opposite side over here. So that's this guy right here, and across from the 90-degree corner is going to be the hypotenuse. Oops, let me highlight that guy. And then between theta and the 90 degree, that's going to be the adjacent side. So just like the similar triangles down on the lower left, if we had something to compare them to, like two separate similar triangles, then we could just set up our proportion and cross multiply to find the missing part. But if I was looking for a specific part and I only had one triangle, I can use something like the sine function to compare the opposite leg to the hypotenuse length, and that's going to create a ratio. Now that ratio is always going to be equal to a certain value because all triangles that are similar with that particular angle measurement will have the same ratio value. So our calculators, again, have been pre-programmed with that ratio value. And that ratio value comes from the sine button on our calculator. So we can write this as sine of our angle measurement, whatever it comes out to be, like on that last picture was 31 degrees. And I could say it equals the opposite value over the hypotenuse value. So in our calculator, it's going to tell us what this should equal. And that's going to be equal to our fraction that we are creating from the triangle. And then once we have those two values, we can just solve. We could cross multiply, we could do a t-chart, whatever. Okay, now that's if we're looking at the opposite side and the hypotenuse side. But sometimes we're looking at two different sides. So this next one, the cosine value, which is the CA abbreviation, C stands for cosine, is going to be when we compare the adjacent leg, that's this A here, to the hypotenuse length, the H here. All right, so I'm going to write that down. We're going to have the cosine value of our angle measurement is equal to our adjacent length compared to the hypotenuse length. Again, that cosine value of that angle, when we punch it in our calculator, is going to give us a value that our ratio is equal to. And that's because of the type of triangle it is. So then we just have to set it up equal, cross multiply, or solve with a t-chart. Okay, now that's great. We're comparing opposite hypotenuse or adjacent hypotenuse, but what if we have opposite and adjacent sides on the triangle? Well, in that case, we're going to be using the tangent function. The T in TOA, the abbreviation, stands for tangent. So I'm going to write that down. Tangent of our angle is equal to, and now this one, if you look at the abbreviation O and A, O stands for opposite, and A stands for adjacent. So that SOHCAHTOA is just a quick abbreviation to remember all of these formulas. And again, these formulas are like saying, hey, I've only got one triangle, but I need to figure out the missing part. I don't have something to compare it to. So let's let our calculator tell us what it should be equal to and then solve for that missing part. All right, I'm going to jump over to my calculator here if I can. Let's see, calculator. There it is. Okay, so on my calculator here, this is a graphing calculator, so yours might look a little different, but we have our sine, cosine, and tangent buttons right in the middle. And if I want to access them, I have to make sure that I'm in the right mode. I don't know that I have a little laser pointer that I can show you, but up at the top button here, top row, I guess not the row next to the screen, that's all of our F1, F2, F3. We don't want those. We have the blue second button, and then next to it we have the mode button, and I'm going to click the mode button. And it brings up all of these different types of settings. And the only one that we need is the third one down on the left. It says radian currently. Over to the right of that, it says degree. So I'm going to click down. It's blinking on radian. I'm going to click over to blink on degree, and then I'm going to hit enter. And it should highlight the degree word. And that's because we are calculating our angles in degrees. Radian is just a different type of measurement. All right, I'm going to clear out of this, and now my calculator is set up. So I've got this sine button, or I've got a cosine button, or I've got a tangent button. And those are going to help us find what the ratios should be equal to. All right, I'm going to jump back to our notes here. Let's go to our first example on the next page. And on this first example, the first thing we want to do is we want to set it up, using the abbreviation SOHCAHTOA. So we're going to have to label the parts that we currently have. We're not going to label everything. So I'm going to look at where is my angle measurement. Now this is only on a right triangle, so we always have a 90-degree corner. But I can see that I have an angle measurement listed right here, 20 degrees. So now I want to use the 90-degree angle and the 20-degree angle to identify what sides we have, opposite, adjacent, or hypotenuse. So looking across, I can see that there is a 410 length over here. That length is opposite of the 20-degree angle. So I'm going to put an O for opposite. I can see the X length right over here. And that is across from the 90-degree corner, which makes this the hypotenuse. Now the other side doesn't have anything listed, so I don't need to worry about it. So now thinking about SOHCAHTOA, I can see that I have an O and an H, and with SOHCAHTOA, I see that the O and H are only located in this first abbreviation part, which means I'm going to use the S for the sine function. So this is going to be a sine function. Then we're going to put our angle measurement. We're going to put equals. And then I got to remember, how do I set up that ratio that's going to be equal to that sine value? And if I look up at the SO part, O comes first, which means our opposite number is going to go on top. Then the H comes next. That means our hypotenuse number is going to go on the bottom. Now, right now, this doesn't look like anything we're used to, but I can always create another fraction by dividing by 1, because dividing by 1 does not change it. And now we have two fractions. And that's exactly the same as what we did on our last chapter. Two fractions, and then we cross-multiplied to solve. So I'm going to cross multiply. Okay, now when I cross multiply to start, I can see it's going to be maybe this direction. 1 times 410. 1 times 410. Okay. And then I'm going to go the other direction. And let's see, I'm going to choose a different color here so you can see it stand out. X times sine of 20. All right, now this looks kind of weird because it's not just numbers and the letter X, but we're just going to solve like we would typically on a equation here or a t-chart. So 1 times 410 is just 410. Oh, I'm going to rewrite that. 410. And then x times sine of 20, well, I can just rewrite that as x times sine of 20. I could figure out what the sine of 20 is, but more often than not, when we had those ratios, they weren't great decimal answers. So I'm just going to leave this as x times sine of 20. Now, sine of 20 is kind of just like a number, so I'm going to keep that together. Whoops, kind of taking up too much space here. Let me erase this for more space. All right, now 410, that's great. I'm going to do a little t-chart here, and I'm going to get rid of this x times sine of 20, which means I got to get rid of this times sine of 20. Opposite of multiply is divide. So I'm going to divide by the sine of 20. And when I do that, my sine of 20 will cancel each other out because multiply and divide are opposites. The x value will drop down. And then I need to physically type into my calculator 410 divided by sine of 20. So I'm going to go back to my calculator. I'm going to type 410 divided by sine 20. Now my calculator gave me a parenthesis in front of the 20, so I should close it with a parenthesis after the 20. And I'm going to hit equals. And here it comes out to an ugly number, but we can round it to the nearest tenths, let's say. So this would be 1,198.8. So if I go back, 1,198.8-ish. And if I look at the original picture, I don't see any units of measurement listed, but this could be like feet, meters, whatever. But that's going to tell me the length of our missing hypotenuse. So this x right here is now 1,198.8 units long. And that does seem reasonable because the hypotenuse on a triangle is always longer than the legs of a triangle. And 1,198.8 is longer than the number 410. So here we were able to solve for a missing side on the triangle without using Pythagorean theorem, without comparing it to a similar triangle, and that's because all triangles with this 20-degree angle measurement and a 90-degree corner will always have the same comparison using that sine function. All right, let's try another one. So this next one is looking at, again, a right triangle, but here we have a 35-degree angle, and we're missing a side, and we've got a side listed as 515. So I'm going to identify what we have first. Here we've got a 90-degree corner. Across from that, this length would be the hypotenuse. And then I've got this length here listed as 515. The 515 is next to the given angle and next to the 90-degree angle. So this would be the adjacent side. So this time we don't need to worry about the opposite side because we are looking for the hypotenuse and we have the adjacent side. So with A and H, if I go back up to this SOHCAHTOA, I can see that Ka is the only one with A and H. So this is going to be a cosine function. And then I'm going to put my angle measurement, and then it's going to be A over H because A came first and then H. A is 515, H is the unknown. Now again, I can make this into a proportion simply by dividing by 1 underneath my trig function. And then we're just going to cross multiply. So when I cross multiply, I'm going to be doing 1 times 515. And that is going to be equal to x times cosine of 35. All right, 1 times 515 is just 515. And it still equals x times cosine of 35. All right, I'm going to do a t-chart. I want to get rid of this times cosine of 35. So we will divide by cosine of 35 on both sides. The cosine of 35s will cancel out because opposite of multiply is divide. Excuse me. And then again, I write too big and I run out of room. So if I solve this out, the x will drop down, and then I physically type in 515 divided by cosine of 35. So I'm going to go back to my calculator. 515 divided by cosine, oh, and I forgot what the number was, 35. Close my parenthesis, hit equals. All right, this one comes out to 628.7-ish. 628.7. So if I go back to my picture here, that hypotenuse length right here is a length of 628.7 units long. And again, that makes sense because the hypotenuse should be the longest, and it is definitely longer than 515. All right, now let's say that you are doing all of this stuff and you're typing it in exactly on your calculator and it's coming out to a different answer. That is simply because your calculator is set up for a different unit of measurement. So just like centimeters and feet are different, degrees and radians, which we haven't learned about yet, those are different units of measurement. Depending on the type of angle measurement, the unit that you have, your calculator is set up to calculate for both of them. And so you are just calculating it in the wrong units. And you'll have to make sure that you can change the mode of your calculator to satisfy the current one that we're doing, which is degrees. All right, let's go down to example 3. This one again, I'm going to abbreviate SOHCAHTOA as my reference. Here I can see that I've got a length over here, and that is next to the angle measurement. It is next to the 90 degrees, so this would be the adjacent side. And then I have another measurement down here. That's the one we're looking for. That is across from the angle measurement, so that is opposite of the angle. So with A and O, we can see that we are going to be using TOA, which is the tangent function. So I'm going to zoom out a little bit here. Tangent. Next to that always goes your angle measurement. This is 65 degrees. And then I'm going to do the O value, the opposite, divided by the adjacent value. So that would be the unknown x divided by the adjacent value, which is 30. Again, because this is a nice ratio on the right, I can create another ratio on the left and then just cross multiply. Okay, 1 times x on the left, and then the other direction, we've got 30 times tangent of 65. All right, now this is a little different because our variable is over by the 1. And so with this one, 1 times x is just x. And now it says x equals, which is great. I don't have to do a t-chart. So I just have to type all of that into my calculator. 30 times tangent of 65. So I'm going to go back to my calculator. 30 times tangent of 65, close the parenthesis, equals. Comes out to 64.3-ish. So 64.3. And that's it, because I already have it saying x equals. So this x length is 64.3 units long. Now for this picture, it wasn't talking about the hypotenuse. And the two legs, those ones don't have to be bigger or smaller than each other, in a certain way. So I just need to look, is it looking reasonable for this picture? So I can see that the 30 length does look shorter than the 64.3 length, but be careful because not always are pictures set up to look to scale. All right, looks like we've got a few more examples here. So I would like you to pause at this moment and try solving for these other examples using the same method, because I've just shown you one of each, and then I will put up the answers and you can check your work. All right, so I'm going to pause. So don't freak out. Just need to pause. All right, let's see what we've got. So I hope that you paused and actually tried these out, because if you're just copying, it's not going to sink in like it would if you tried it and made a mistake. Making mistakes is a really important part of the learning process. So here you can see all of my work and the answers. So again, don't just copy. Make sure that you've tried these. If you're struggling and you got it wrong, make sure that then you look at my work and say, how did she get those values? Like on this first example 4 here, I looked at the sides that I was missing. This O side that I labeled, that's because it's opposite of the 72. And then this guy here, the X, it was next to the 90 and next to the 72, so that's the adjacent. So make sure that you're looking to see, how did she label them? Did I label them correctly? Did I choose the right SOHCAHTOA abbreviation? And all of that good stuff. All right, so then there's a summary here. What two parts of a triangle are needed to find a missing side? So if you were doing Pythagorean theorem, you could just have two other sides to find another missing side of a right triangle. But if you have one side length given and an angle measurement given on a right triangle, then you can find another missing side. Okay, now for your homework, these are not things that you can do just in your head. You'll need to write them down as a proportion and do cross multiplying. So here's a nice, great blank space for you.